Okay, welcome. Let's see a few exercises from section 2.4. The first exercise we're going to do together is exercise 73, which asks us find the constants a and b such that the function is continuous on the entire real number line. So we have a function that is given piecewise. So we have three rules. We have f of x equals 2 if x is less than or equal to -1, f of x equals ax plus b if x is between -1 and 3 not included, and f of x equals -2 when x is greater or equal to 3. So let's see how we're going to solve that. Firstly, when we have a problem like that, we should sketch the information we have, and in that case we know that f of x is equal to 2 when x is less than or equal to -1. So if we simply start with a system of x's and we just write x -1 here, and we know that f of x equals 2. So it's a full dot because x equals -1 is included. And now the third rule tells us that if x is greater or equal to 3, f of x is -2. So 1, 2, 3, -1, -2. So from here on with a full dot as well, because x is also equal to 3, the value of the function is -2. And now we have the middle rule, which is the one that we need to find a and b for, and we need to do that in such a way that this function is continuous. So it could be many things. It could be a function like that, and actually in the near future we're going to have similar problems where we want these three pieces to connect smoothly, so we don't want sharp turns. We would like maybe something to turn like that and then nicely connect here so that it's not only continuous but also differentiable, so no sharp turn. But for the moment, what we're going to need to find is a line. So it makes angles here and it makes another angle here. But the question is, what is the equation of this line? So when we're looking for the equation of a line, we want a point and we want a slope point. We may take any of these 2 points that we are given. We know one here, -1, 2. We know another point down here. This is the point 3, -2. We can take whichever. I'll just pick -1, 2, and slope. So to find the slope, I'm going to do rise over run with these 2 points. So it's -2 minus 2 divided by 3 minus -1, -4 over 4 equals -1. It's a negative slope. Does it make sense? Yes, it does, because it's going down. If you were thinking, well, I don't need the slope, I have 2 points, that's great. You can find the equation of a line in many different ways, but in AP Calculus AB, I insist that you should very quickly adapt to the fact that we want to write equations of lines in point-slope form. So here, the equation of the line we're looking for is y minus 2 equals the slope times x minus -1, right? So in 90% of exercises, this is the final answer. You found the equation of the line. You don't need to go any further. Here, actually, we do need the slope-intercept form, ax plus b, so we have to do a little bit more work. This is minus x minus 1, and so y equals -x plus 1. Alright, so we found a is -1, and b is equal to 1. We're done. The second exercise I want to discuss is question 79, and for this question we have to find the continuity of a composition of functions. So if you look at f, it's 1 over x minus 6, so it's not continuous at x equals 6. And g is x squared plus 5, that's a parabola, so we need to know that it's a continuous function. Actually, we need to know that polynomials are always continuous. And again, in the near future, when we talk about derivatives, polynomials are always differentiable as well. Right, so let's see how we can solve this question about the composition of functions. So we have f of x equals 1 over x minus 6, g of x equals x squared plus 5. What about h of x, which is f of g of x? So there are kind of two ways we can do that. The first method would just be to find what h of x is and then solve. So let's do that. Method 1, h of x equals 1 over, and then it's not x minus 6, but it's g of x minus 6, so x squared plus 5 minus 6. And this is 1 over x squared minus 1. So we notice that the function is continuous. H is continuous everywhere except at x equals plus or minus 1. The second method is, it boils down to the same thing, but you can just look at g of x. You see it's never discontinuous, it's a polynomial. You notice that f of x is discontinuous at x equals 6, so you may want to just say, okay, when is g of x equal to 6? 6 equals x squared plus 5, and then you solve this, x squared equals 1, and of course you get the same answer, x equals plus or minus 1. So h is continuous everywhere except at these 2 points. So I'm not copying this again, but if you only solve with method 2, you need to answer the question. H is continuous everywhere except at x equals plus or minus 1. So exercise 117 is definitely a step higher in the difficulty, and I'm not surprised if when a student or even a teacher reads this exercise, they feel a little bit confused. It seems very difficult. So a long-distance phone call service charges 40 cents for the first 10 minutes and 5 cents for each additional minute or fraction thereof. Use the greatest integer function to write the cost C of a call in terms of time t in minutes. Sketch the graph of this function and discuss its continuity. In spite of the fact that they tell me to find the equation first and then graph the function, I am definitely going to want to graph the function first. When I see the function, it seems so much easier to me to figure out how to set up an equation for the function. So if I don't call, that's pretty obvious, I'm not paying anything. You can actually ignore this if you want. For values of t, let's call this t, or shall we call it x? Up to you. Let's call it x just because we're more comfortable with x. And y is the cost. So x is the time. For negative values of x, if you call a negative number of time, it makes no sense. If you want to put a 0, that's fine. If you want to say it's undefined, that's fine too. Then what do we know? As soon as you start calling, you pay 40 cents, $0.40. And there you go. For the first 10 minutes, you're going to pay 40 cents. It doesn't matter if you called 1 second or you called 9 minutes 50 or if you called exactly 10 minutes. And as soon as you pass 10 minutes, you pay 45 cents. 0.45. And if you go beyond 11 minutes, then you're going to pay 50 cents. And so on. So it helps me to have the graph first, because at least now I recognize this looks a lot like the greatest integer function, and I can hopefully move the greatest integer function around and make it fit to this graph. So if we call this function f, I'm not sure if it had a name, maybe it was called c for cost, but whatever, f of x equals, well, if we want to say that a 0 minutes costs $0, we can just say it's 0 if x equals 0. If you don't do that, that's totally fine, because it's really common sense. Now, for all values of x between 0 not included, we put a circle, and 10 included, so between 0 not included and 10 included, the price is 0.4 or 0.40. And after that, I need to figure out a way to express this ladder. So how can I do that? I want a price of 10.5, for example, to give me an extra 5 cents. So I think it's safe to try and say, okay, x, if I take the greatest integer function of 10.5, it's going to give me 10. That's not what I want. I want 1 extra time of 5 cents. This is going to tell me how many times I want 5 cents more. So what I need to do is my number of minutes, 10.5, I need to subtract something from it. I want the result, if I plug in, for example, x equals 10.5, I want the result of the whole thing here to give me $0.05. So the first thing we may think is it's x minus 10. But actually, if you think a bit further, if you call 10.5 minutes, 10.5 minus 10 equals 0.5, and the greatest integer of 0.5 is 0. So that will not allow me to add 5 cents. It's actually minus 9. Let's check. If I know that if I call 11.5 minutes, I should be paying 50 cents. So let's see. 11.5 minus 9 equals 2.5. I take the greatest integer of 2.5, it's 2, and then it's 2 times 5 cents. So that's great, but I forgot something. I only found the increments, but I forgot that I'm still paying 40 cents from the beginning, so I need to add 0.4. So from values of x greater than 10, this is what you can do. Now, the reality is this answer is not quite correct. If you manage to see why, then really congratulations. This is the reason. The greatest integer function actually looks like this. So the greatest integer function always includes the leftmost point of the interval, and on the right it's the jump already. So if I have x equals 1, the value for 1 is up here. If I put x equals 2, the greatest integer of 2 is up here, it's 2. If you look at our graph, the point that is included is always the one on the right, not the one on the left. So that's a technical problem that we can discuss. We can do two things about that, actually, if we really want to go further. One thing is you can cheat. You can say, well, this is true, my rule, if x is not an integer. And you can add another rule, and this other rule will be true for all values of x greater than 10 if x is an integer. So let's see what we want this rule to be. So let's pick 11. For 11, we want the result to be 0.45. Had I put 11 here, I would have gotten 11 minus 9 equals 2. Greatest integer of 2 is 2. 2 times this is 0.1. And 0.1 plus 0.4 equals 0.5. So it would have given me this point up here instead of that point down here. So how can I do that? I need to fix that. Well, if x is an integer, what I need to do is the number of time I need to multiply 0.05 is actually, I don't care about greatest integer anymore because it is an integer, but I think this time I need to subtract 10. And of course plus 0.4. Let's check to see if it works for x equals 11. 11 minus 10 equals 1, so I'm adding 1 times 0.05. So if you add this third or fourth row, this fourth rule for x's that are integers, then you have the perfect graph. Now you may wonder, is there any way to do this in a more elegant way? Because I think any of you can realize this is not so pretty. To make just an additional rule like that is not so pretty. So the question boils down to, can we somehow flip these two in the greatest integer function? Is there any function g where we would have whatever, but the circles, the empty circles on the left and the full dots on the right? And I'll show you how to do that, but I'm not going to resolve the exercise. If you're interested, you can do it yourself afterwards. So the thing is, we need to use some transformations. If you graph the function negative x, the integer function of negative x, what you get is actually you're flipping across the y-axis. When you're looking for the value at x equals -3, you actually look for the greatest integer at +3. You're flipping the value of negative and positive. What that does, it switches everything like that, is that your graph is now going to look like this. So I just drew this, but I flipped it to the other side. And this one here will find itself here. And this one up here will find itself there. And this one here, flipped to that side, is going to look like that. So that function is when you take the greatest integer of negative x. Furthermore, because we're not too happy this graph is going down, we can now add a negative in front. What does the negative in front do? It flips across the x-axis. So we end up, if we have g of x equals negative greatest integer of negative x, with a graph that looks like this. So from here, if you were determined to find a nicer answer than we have up here, you can now figure out a way to move these stairs, which have the correct orientation so that they fit here. Okay. So that was a very difficult exercise. One more question we're going to do together in 2.4 is question 121. Use the intermediate value theorem to show that for all spheres with radii in the interval 5, 8, there is one with a volume of 1,500 cubic centimeters. The reason why I want to do this exercise is that it's a little bit weird. It feels like it's an easy exercise. Why are we asked to use the intermediate value theorem? And it's true. It's a little bit of an artificial exercise, but I want to do it the way they expected us to do it. So, the volume of a sphere is 4 over 3 pi r cubed. And we know that we are looking for radiuses that are between 5 and 8. This sign here, which is like this, means is included. So the radius is included in the interval from 5 to 8. So what we can do, after all, the question is there exists a radius between 5 and 8 such that the volume is 1,500? So what we can do is solve this, multiplied by 3, 4,500 divided by 4, divided by pi equals r cubed, and I get r equals the cube root of 4,500 over 4 pi. So let's grab our calculator and just do that. Okay, so up 3, 4,500 divided by parenthesis 4 pi. I'm putting the parenthesis just in case because it may only do 4,500 divided by 4 and then times pi. And we find that r equals 7.101. So in AP Calculus you always want 3 decimals. You can round them or truncate them. If you don't have all the decimals you need here, then you need to fix your settings. So we basically answered the question. Yes, there is a radius between 5 and 8 such that the volume is 1,500. That radius is 7.101. What they actually wanted us to do is to check what is the volume, what is V if R equals 5, and what is V if R equals 8. So if R equals 5, the volume is 4 over 3 times pi. Let me show you something really interesting here. Times r cubed. And now I'm going to say with the control button here, control, oops, did it come? No. Oh yeah, control, and I take this vertical line here. Now I can say what I want r to be. R equals 5. And if r equals 5, the volume is 523.598, or if I round up, 599. So you can round to 599 or you can truncate to 598. So here's why it was useful to use that. Now instead of retyping everything, I can just change the end and say what is 4 over 3 pi r cubed when r equals 8, and the answer is that the volume is 2144.661, or 660 if you truncate. So we can't see super well on the calculator, but these are my results. So what they wanted us to do is to say that the volume is a continuous function of r. The volume doesn't jump if we change r gradually. So since the volume of 5 is 523.599 and the volume of 8 is 2144.661, the IVT assures us that there is a value of R between 5 and 8 such that V of R equals 1500. I cannot go from 500 to 2000 without going through 1500. Really logical. But it's important to say it's because it's a continuous function. If the volume wasn't continuous, I could be at 500, and then jump and end up at 2000 without going through 1500. But since it's a continuous function, I must somewhere go through 1500. Okay, so here's for these 4 more difficult exercises. It's very good preparation for the future. Thank you for listening.